So, application for atoms. When we talk about relative kinetic energy or the internal energy for an atom, we're essentially talking about the kinetic energy of the electrons. Why is that? Because we're talking about the motion or the kinetic energy associated with the reduced mass. And the reduced mass is essentially the electron, right? So 1/2 mu v squared is essentially equal to 1/2 mass of electron v squared, we could say. Okay? And it's also customary to assign the potential of energy of the atom to its electrons. In other words, potential energy should really be defined in terms of two particles that are interacting. Okay? But as a matter of convenience, we're just going to say, okay, we can treat the electrons as having all the potential energy. We're just going to assign all the, it doesn't really matter how you partition your energy as long as you have the same total. So we're just going to say, let's assign the potential energy just to the electrons. And so we can now write the total energy as simply the kinetic energy of the due to the center of mass. That's the movement of the atom as a whole. That's essentially the potential kinetic energy of your nucleus, the movement of the nucleus. And the relative energy, okay, then we can say, due to the internal motion or the relative motion of the electron to the nucleus, well, plus the potential energy of interaction between the proton and the nucleus, that will essentially, that's what we would call your electronic energy. Okay? So kinetic energy of the nucleus is essentially the kinetic energy of the free particles. So if you treat this system using quantum mechanics, you'll have, the nice thing is when you set it up, when you set up your Hamiltonian in quantum mechanics for this two-particle system, you have a proton and an electron. Okay, then you can pretty much say that the kinetic the kinetic energy operator for the Hamiltonian that depends on the center of mass is essentially that of the nucleus. The location tracks the nucleus. So that just gives you, and then you have a part of your operator that's just going to depend on the coordinates of the electron, essentially, the coordinates of the reduced mass. So you have what's called separation of variables, again, like we saw last time. Okay? So what we would call the energy of the atom in general is really just the energy of the electron, the electronic energy. Okay? So typically, the movement of the nucleus as a whole, the atom as a whole, is just the movement of the nucleus. We can just think of that as a free particle problem. Okay, so we've set what we end up doing in quantum mechanics is we have a problem that involves a proton and a nucleus. We simplify that into two simple problems. One problem describing the nucleus, which is a free particle problem, and another problem which describes the electron. And that's the one that we need to solve in the next PowerPoint. We're going to talk about the hydrogen atom. And that's why when you talk about the energy of the hydrogen atom in your freshman chemistry classes, you keep talking about electrons just jumping from one orbital to another, because you're really just talking about the electrons when you're doing that. Okay, you're ignoring the movement of the atom as a whole. You're looking at the internal motion, the motion of the electron relative to the nucleus. All right. So for an atom, like I said, the total energy is just the kinetic energy due to translational motion of the nucleus. So that's just the kinetic energy of the nucleus, and kinetic energy due to the motion of the electron, which is really the motion of this reduced mass. Okay? So your Hamiltonian would just be a kinetic energy operator due to the nucleus plus 1. A kinetic energy operator due to the electron, let's just pretend we have one electron to make things simple, plus the potential energy of interaction, which is just going to depend on the distance of the electron from the nucleus. Okay? So this part right here of your Hamiltonian depends only on the reduced mass coordinates. So this only depends on essentially the coordinates of the center of mass, okay? I'm sorry, the reduced mass. The reduced mass, and what's the reduced mass here? It's just the electron, okay? So The Hamiltonian for the nucleus is this one right here. Okay, depends on the center of mass, and this is your the part of your Hamiltonian that affects the electronic coordinates, depends on the relative coordinates. So again, here we see a Hamiltonian that affects one set of variables plus, so you have that it's composed of an operator that affects one set of variables plus another operator that affects another set of variables. So the eigenfunctions of this can be written as a product of two functions. A function that depends only on one set of variables times a function that depends only on the coordinates of the other part of the reduced mass. Okay, so in this case, what would be our psi for our nuclei, or for our nucleus? Free particle, or if your atom is in a box, it's going to be a particle in a box wave function. So you're just going to say it's going to be square root of 2 over whatever the length of the box is, right? Sine. Remember the formula? Okay. N pi x over L if it's a one-dimensional problem, and you can just extend this if you're doing 3 dimensions. Okay. So anyway, so we already know that part of the problem. So our focus when we start looking at the Schrodinger equation as applied to atoms is when we solve it, we're really just going to be interested in the wave functions for the electrons. And those wave functions for the electrons, you've encountered them in your freshman chemistry, you call them atomic orbitals. Okay, so those atomic orbitals, those are really nothing more than the electronic wave function for your atom. Right? So from now on, when we talk about atoms, when we say H psi equals E psi, keep in mind, okay, that this Hamiltonian really refers only to the electrons. We're just going to factor out the center of mass problem from our problem, from the overall problem for the atoms. And whatever we call the energy of the atom is really just the electronic energy. The total energy should really be whatever that electronic energy is plus the translational kinetic energy, plus the kinetic energy due to the motion of the nucleus. Okay? And what we would call our wave function is really nothing more than the electronic wave function, because we say the electron is essentially the center of mass, the reduced mass. Reduced mass is essentially that, the electron.